And now I want to introduce Matt Kaye, who is a professor from Northwestern University, and he is also the co-director of the Midwest Uncertainty Collective, or MU Collective. And Matt's research focuses on ways to communicate uncertainty, which is increasingly crucial given all the data we're inundated with on a daily basis. I'll let him make the case for that and turn it over to Matt now.
Thanks, Wendy, and thanks for having me. This is very exciting and hopefully going to be fun. Let me do the usual song and dance of sharing my screen. Okay. Yeah, so I'm Matt Kaye. I'm assistant professor in the School in Computer Science and also in Communication Studies at Northwestern University. Previously, I was in the School of Information at the University of Michigan, and before that, I did my PhD at the University of Washington. I work broadly in HCI and a lot of things lately in information visualization, and over the past several years, specifically in uncertainty visualization. And today, I'm going to talk about what I call uncertainty visualization as a moral imperative, which I'm going to try to make a little bit clearer as we go along. So there's kind of two strands of work that I do lately. One of them is in this question around what kinds of uncertainty visualizations should we build, and how do we figure out what makes a good uncertainty visualization? The other one is in tools for constructing effective uncertainty visualizations, and I'll get more into that one in a couple of minutes. But I want to start here with this question of what kinds of uncertainty visualizations should we build? So I want to go back to the 2016 presidential election. So not the 2020 presidential election, which Trump lost, the 2016 presidential election, which he won. So in 2016, there were several poll aggregators trying to predict the outcome of that election, to taking information from polls across the country, putting them through statistical models, and then trying to give a probabilistic prediction of Trump's chance of winning that election. 538, one of those poll aggregators, gave him a 28% chance. New York Times gave him a 15% chance, and the Huffington Post a 2% chance. Now, the interesting thing is, this many years later, people still think that 538's prediction, for example, was a bad prediction. Because Trump won, and they gave him less than a 50% chance of winning. Well, the problem is you can't really judge a probabilistic prediction that way on the basis of the outcome of one event. So one way you can judge a probabilistic prediction is by something called calibration. So you might ask a question like, when 538 over all of the predictions that they make says there's a third of a chance of something happening, does it happen a third of the time? It turns out for 538, they're relatively decent at calibration. So generally speaking, if they say something has, say, a third of a chance of happening, it'll probably happen in about a third of cases. So we can't necessarily say that this single prediction is a bad prediction. But what I would contend, and kind of from the HCI perspective, is if people are getting mad about this and thinking that it's a bad prediction, then there's probably something wrong with the way that it's being presented. So here's a different way of presenting the same information. This is something called a risk communication theater. The idea here is I've given you a ticket to a random seat in this theater. I've colored the seats black in proportion to Trump's chance of winning. So there's about 280 black seats in this 1,000-seat theater. If you end up in a black seat, Trump wins the election. If you end up in a white seat, Clinton wins the election. I hope you agree with me in this particular alternative presentation that you find it a little bit less surprising to learn that Trump won the election than when I just told you that he had a 28% chance. So the idea here is really that people are good at ignoring uncertainty, but this is especially true when we provide bad uncertainty representations. Risk communication theaters are just examples of something called icon arrays. They're used in medical risk communication and to communicate things like chances of different outcomes of different potential treatments for some condition, say. More generally, we call these frequency framing or discrete outcome visualizations of uncertainty. So rather than saying, there's a 28% chance or what have you, I'm showing you a grid of possible outcomes and then coloring them in proportion to different chances of those different outcomes. There's a lot of literature sort of in the medical risk communication field and in the uncertainty visualization field suggesting that these make it a little bit easier for people to make better decisions from uncertainty visualizations. So One of the things that I worked on several years ago now is this question of what is an icon array for a continuous distribution. So this is a discrete distribution. It has discrete possible outcomes. In this example, successfully cured of angina or not. Or in the election example, Trump winning versus Clinton winning. What's an icon array for a continuous distribution, a variable like, say time or something like that? So I'm going to give you an example scenario and kind of walk through how you might try to construct such a visualization and the sorts of properties that it might have. So this is a photograph of a system in Seattle called One Bus Away. It tracks where all the buses are in Seattle in real time, and it tries to predict when they're going to show up at the bus stop, right? Obviously, there's uncertainty in this system. GPS tracking can be unreliable in urban areas with tall buildings. Traffic introduces uncertainty into how long it's going to take the bus to get from wherever it is to wherever you are, and so on. But this particular system right now is telling me the bus number 120 is going to show up 11 minutes from now. It's under a 6-minute delay. This kind of text you can see right there. It is giving me some uncertainty information, sort of. So if I read down at the bottom, it says bus arrival estimates are based on the best available information, but actual times will vary. This is, not really that useful to me. I might have a question like, do I have time to get a coffee before the bus shows up? There's probably about, if this was in Seattle, there's probably about 3 coffee shops within eyeshot. Can I run over there and get back before my bus shows up? Well, right now the system is telling me something like this. So here's a timeline. 0 is now, off to 30 minutes from now. The system is saying your bus is going to show up exactly 11 minutes from now. Well, this is not really all that useful to me. What I really want is something maybe more like this. So this is a probability distribution over time to arrive at the bus. So there's a, not unreasonable chance it shows up somewhere between maybe 6 or 7 minutes and 10 minutes from now. It's most likely to show up 11 minutes from now. You may not be able to see it, but there is a bit of a skew here. So, maybe it even shows up 15, 20 minutes from now if the bus gets stuck in traffic or something like that. But, this is really not the information that I need either to answer that question of do I have time to get a coffee? Or really, what's the chance that I'm going to miss my bus? What I really want to know is something like this. If I show up at the bus stop 8 minutes from now, there's a 90% chance that the bus comes after me, which is the same thing as saying that I catch the bus. If it comes after me, I get it. If it comes before me, I don't. So you might say something like, okay, if I'm designing a user interface to communicate this probabilistic sort of prediction to people, I'll choose some kind of risk threshold, like 90%. And then I'll construct this one-sided interval, and I'll tell people the bus is going to show up 8 minutes from now. Well, the problem there is that risk preferences vary, both between people and then also within individuals over time. So I might be going for a very important meeting. My risk tolerance goes down to 0, and I need to show up, 5 minutes from now in order to make sure I catch the bus. I might be getting lunch with friends, and maybe it's okay if I'm a little bit late, or maybe I know there's another bus I can catch, and so that goes to more like 75%, and I'm quite willing to get there 10 minutes from now or something. So the point is that what I really want is some way of representing this information to people such that they can apply their own sort of risk preferences on top of the information that they're getting to make an informed decision kind of in the moment. So one thing you could say is, well, I'll just show people this density plot and allow them to kind of estimate approximately, is this how much this sort of area is as a proportion of the full area. Maybe it's about 90%. So that's my risk tolerance, and maybe then I'll go to the bus stop 8 minutes from now. But it turns out that area perception in humans is not great. So I'm gonna do the one interactive part of this talk. Hopefully there's 3 people paying attention. I want someone out there, maybe just in the chat, who hasn't seen a demo like this before, so you don't know anything about area perception, so you can't cheat, to just tell me how large you think this small inner circle is as a proportion of the total area of the outer circle. So that full area, how much is this thing as a proportion of this thing? 85, 90, 90, 80. Yeah, so you're all guessing in the right ballpark for how everyone gets this wrong. So I see someone said 75%, which is the actual correct answer. The interesting thing about area perception in humans is that it's biased. As things get larger and larger, we don't perceive them as being as large as they actually are relative to the smaller objects, which means that you see this larger outer circle as being a little bit smaller than you should relative to the inner circle, which means the proportion of the smaller to the larger is larger than it should be. So it's about 75%, and you probably see it as being more like 85%. So density chart, maybe not the best idea here. One alternative is to take the integral of this thing. And if you happen to forget what that means from calculus from however long ago, basically that just means that, say, at the 10-minute mark, this function up here is going to tell me how much of the area is to the left of 10%, what proportion of the area. So if I read up and then read over, it says 25% is to the left of 10 minutes. And so probably about 75% is to the right of 10 minutes. But I said before that what I wanted to do was sort of try to take advantage of this like frequency framing approach to uncertainty visualization. Because we have some idea that people are better able to reason about uncertainty under that kind of representation. So I'm not going to use this kind of CDF thing. What I'm actually going to do is I'm going to take equally spaced values in probability space and then project them back into time, and then stack them up into something called a dot plot, which really is the kind of continuous analog to an icon array. So you can do the same sort of counting reasoning that you would with an icon array to answer questions about the chance of things happening. So what does that look like? So for example, if I know that there's 20 dots here and I count up 2 from the left, and say, whatever this is, 8 minutes, I've missed 2 out of 20 of these hypothetical buses. I've caught 18 out of 20 of them, right? 18 of them are after me. That means that there's an 18 out of 20 or 20% or 90% chance, sorry, of me catching the bus if I show up at the bus stop 8 minutes from now. What's also really interesting about this representation is you can do something called subitizing. So subitizing is just our ability to essentially instantaneously count the number of objects in small sets up to about 5 or 6, right? So these playing cards, I haven't labeled them. Well, it's actually a photo of old school playing cards that used to not have numbers on them. And you can immediately recognize like this is a 5 of spades, right? Well, the cool thing here is if the probabilities I care about are in the tail of the distribution, and I've chosen, a relatively low denominator for this dot plot, it's very easy for me to find these tail intervals, because I'm just counting like sets of 2 or 3 things in order to find where these intervals are in the tails. So we've done a couple of different sorts of studies on these things. One of the things that we found is, as we would expect with sort of this kind of subitizing estimation approach, people are able to make better estimates of these tail probabilities compared to other things like, say, density plots. But the real question here, and the trick with uncertainty visualization, is even if people can pull out the number from a visualization that should be able to tell them or should give them the information that they need to make a better decision, it doesn't necessarily mean that they know how to use that information to make a better decision, right? This is really the problem with uncertainty visualization often. Do better perceptual estimates actually lead to better decisions? Oh, someone's asking, what's that word I'm saying? There you go. So really, what we did is we said, okay, let's actually set up some incentivized decision-making experiments, where we show people things like one of these interfaces for a probabilistic prediction of when the bus is going to show up, give them incentives for things like, we'll take some money off of your payout for every minute you're at the bus stop because waiting at the bus stop is boring. We'll add some money to your payout for every minute that you're at home watching TV. We'll give you a bonus if you get to your meeting on time. Here's a probabilistic prediction. When do you want to go to the bus stop? What we see is, and I just have to make sure I'm actually back on this screen again. what we see when you do that is that we do actually get better decisions. So this chart over here is just showing over time estimates of decision quality, actually distributions of people's decision quality over many people, where 1 is optimal in terms of expected payout, and 0 is obviously very bad. And so this is actually just showing the top 40%. And just the ratio. So the closer this is to 1, essentially the better the decisions people are making. Compared to things like, say, density charts, you still get a lot of people down around 60% in terms of the quality of their decisions. You don't get as good learning, and you don't get as high of a mean in terms of decision quality. And we compared this to a number of different things, and really these dot plot approaches and CDF type approaches were kind of better than basically everything else. So really the idea here in general, as a sort of view onto some of the type of work I do in this vein, is that the idea is to combine sort of task requirements. So in this case, knowing, for example, that you want these one-sided intervals, things we know about visualization perception. So things like area perception and subitizing, and things we know about uncertainty cognition. So ideas like the usefulness of discrete outcome sort of framing approaches to uncertainty visualization, and then use those things to construct more effective uncertainty visualization designs. So one thing that was really nice about that was, 4 years later, when 538 went and created their new visualization for the 2020 election predictions, they actually used a sort of dot plot type approach as part of their visual communication. I have it on reasonably good authority that this was influenced by the work that we did, because that was like back in like 2016 or so that we published the first paper on these quantile dot plots. So that was kind of cool to see. Other things in the sort of election prediction vein that I think are interesting to talk about. So I don't know how many people know about the New York Times election needle, or have seen this. So this was a popular thing back in 2016. They ran this as well. So this is an animated visualization of uncertainty. The idea here was, so the New York Times was running this model as poll returns were coming in, and they were updating a sort of predictive distribution for what the vote margin would be between Trump and Clinton. You would load this thing up in your browser, and essentially what it was doing is every 30 seconds they were updating their model, and then in your browser it was continuously animating this needle inside the 50% predictive interval. So the idea was to try to help you kind of experience the uncertainty in what this estimate actually is kind of in real time. It didn't, I think, necessarily totally work that way. A lot of people do not like the New York Times election needle. I think my favorite of these reactions is sort of down in the bottom right-hand corner. The New York Times needle jitter is irresponsible design at best and unethical design at worst, and you should stop looking at it. I actually disagree with this. I think so the New York Times election needle was really designed to try to make you experience the uncertainty in that prediction in real time. And so it made people anxious. And then, of course, they got mad that they were anxious. But the thing is, if you're anxious about something that you care about, if you're uncertain about something that you care about, you probably should be anxious, right? But I think there was another issue with the New York Times election needle. So on one hand, it was an effective piece of communication in that it made a lot of people have to experience some uncertainty, which, made them anxious about something that they cared about, but in a way that is really, meaning that they're grasping in some sense the uncertainty in that prediction. But there was another sort of issue to it, which was some people didn't kind of realize that the intent of the jitter was to communicate uncertainty. So they would do things like look at the source code and say, well, it's just random jitter. They're lying to us, right? And I think part of it is that people misunderstood the New York Times election needle as being a thing that was trying to communicate real-time updates in the model. When the model was only updating every 30 seconds, the jitter was just the current uncertainty that the model has. And part of this is I think, related to something that we call in uncertainty communication a deterministic construal error, which is when people misinterpret some aspect of an uncertainty presentation as being about something deterministic. So in this case, real time, like to the millisecond model updates, versus being about communicating something about uncertainty. In this case, say like the current uncertainty in the current estimate. And part of it is almost this sort of, you're imagining like, what is the mechanism behind this needle thing? And when we normally incorporate or encounter these sorts of measuring devices in real life, right, we're encountering them on like scales where maybe the association is more with precision and not with uncertainty. So one of the things that I was thinking about during kind of the intervening years between the New York Times sort of election needle of 2016 and the 2020 presidential election was, what would be an alternative way of presenting the same information? I'll get back to that in a second. And so what I kind of came up with was a different kind of stochastic process that we do encounter, I think, more often. And let's see. The screen sharing is throwing me off a lot. So I built this thing I called Presidential Plinko. The idea was, we've all encountered this kind of Plinko board thing, or something like a Galton board, or a bean machine. These are all these sort of devices where you drop a ball down something with a bunch of spokes, and obviously there's some randomness to where the ball is going to end up at the bottom. And in fact, given the structure of the board, the more rows you add, the more variance there is in where the ball is going to be at the bottom, right? And you can actually back this out. You can essentially say, given some distribution that I want to try to show to someone, I can figure out how many rows I need in a Plinko board in order to have approximately that distribution show up at the bottom of the Plinko board. So I took the predicted electoral vote distributions from a couple of poll aggregators, in this case, The Economist and 538, and backed out what the height of the Plinko boards would be that could generate distributions that look like that. And so the idea is that you can basically drop balls down these predictive distribution Plinko boards and kind of experience the uncertainty that the forecasters are telling you you should be experiencing on election night. It takes a little while. There wasn't a whole lot of uncertainty. There was certainly a reasonable amount in what the outcome of the 2020 election would be, but definitely less than in the 2016 presidential election. Usually it doesn't take this long for me to, yeah, there we go. So we got at least one. The interesting thing too about this to me is you can also use it to kind of feel like, what is the, how surprised should I feel at what the outcome was relative to what the predictions were? So this up here is showing me the predictive distribution from The Economist before any of the polls were counted. And then where this dropped is actually what the final sort of outcome was on election night. And if you showed me a Plinko board this high and then this outcome, and then said, do I think it's that surprising that this is what happened relative to what the prediction was? I think it's not that surprising. And so it's really like trying to give people a more visceral feel for uncertainty, to just try to give people like a way to experience it and then reason about it a little bit better. One of my collaborators, Jessica Hullman, the other sort of co-director of the Midwest Uncertainty Collective, likes to call these kind of animated uncertainty visualizations hypothetical outcome plots. You're showing different hypothetical outcomes. It also abbreviates to hops, which, things are hopping around is kind of cute. But again, the idea is to try to help people experience uncertainty in order to reason about it a little bit better. Well, and really kind of what I'm trying to get at here is a sort of design mantra for uncertainty visualization. This idea that we should be presenting kind of well-calibrated uncertainty, so it should be accurate and well quantified, that can't be ignored in ways that people can actually understand, in ways that you can experience the uncertainty, or in ways that you can reason about it sort of more intuitively. So the idea here is that animation can help people experience uncertainty, and that this can be fairly powerful. So there was another interesting example of a sort of probabilistic visualization a couple of years ago in 2018 from the New York Times that was using animation in a way that I thought was fairly powerful. So I'm just going to demo this and run it for a second here. I'll zoom in a bit. So I really like this example because I think it kind of forces you to almost experience this kind of blue wave moving down of Black boys who were raised in rich households but did not grow up in the same income quintile, or did not grow up to be in the same income quintile as the household that they grew up in, which I think makes this visualization very powerful. I think I do nitpick on this visualization very slightly. So there's the visualization to me works really well in this sort of left half. When you get over to the right-hand side, it kind of falls down a little bit. And I'm going to try to explain why. So basically, what this visualization over here, if I look at the proportion of blue to yellow in one of these little stack bars, it's telling me the probability of having a particular race given that you have a particular adult income. So this people in this box are in the upper middle class adult income quintile, so the second to the top quintile. But if I sort of look at this visualization and estimate how much blue versus yellow in this box, what it's telling me is the proportion of people in this quintile, or men in this quintile who are Black. But the thing is, from this visualization, that's not actually what this text over here is talking about. What the text over here is talking about, it says most white boys raised in wealthy families will stay rich or upper middle class as adults, but Black boys raised in similarly rich households will not. What this is trying to tell me is what's the chance of having a particular income quintile given that you're Black? What's the chance of being rich given that you grew up Black versus growing up white? So what I actually want to know is the probability of adult income given race, not the probability of race given adult income. This is a sort of subtle point, but it's something sometimes called the fallacy of the transposed conditional, this line here being the conditioning operator, and these two things being on the opposite side of where they should be. So you can still see this kind of probability of adult income given race by seeing how much of the blue is moving down versus how much of the yellow is moving down. So in the animated portion, it still works. In the portion over here, in the static portion, though, I think it's a little bit off. But it's actually not that difficult to fix. If you rescaled these boxes according to how many dots actually ended up in them, then you'd be able to see it by just looking at how much blue is in each of these boxes versus how much yellow is in each of these boxes. So you can kind of total it up. This is how much blue is in each box. This is how much yellow is in each box. So now when you total it up this way, you immediately see there's way more yellow at the top of this. If you grow up white and your parents were rich, it is much more likely that you stay rich than if you grow up black and your parents were rich. Now, maybe I'm harping on this a little bit, but I think the point that I'm trying to make here is that building effective, complex, and correct uncertainty visualizations or visualizations involving probabilities is hard. This is a really powerful visualization, but still in one part of it, I think it could be improved. And this is really not to harp on the New York Times. They have basically one of the best data journalism outfits out there who know their statistics backwards and forwards, and it's still easy to do things like this. And so it's really hard to create effective and correct uncertainty visualizations. Prototyping them takes time. You have to build these complex animations, usually in things like D3. It's brittle. Specifications involve conditional probabilities, which are pain to reason about. And you need to be able to like navigate the design space of these sorts of uncertainty visualizations quickly and effectively in order to sort of see what different possibilities there could be. But you also don't want to sort of design yourself into a corner where the visualization you've created is actually incorrect. And so more recently, the work that I've been doing has been focusing on this kind of tool building domain, trying to build systems that allow people to construct effective and correct uncertainty visualizations. So I've been tackling this in a couple of fronts. So one of them is building libraries for the R, statistical programming language, to take outputs from probabilistic models and help people visualize those outputs. I'm not going to talk about that work too much in too much detail. I'm just going to show you sort of the variety of visualizations you can create with that tool. So I built these two packages, TidyBase and ggdist, which essentially allow you to easily construct a variety of different types of uncertainty visualizations. The work I'm going to talk about more today, though, is something called the probabilistic grammar of graphics, which is work by my PhD student, Xiaoying, where we've really been trying to tackle this question of how do you create uncertainty visualizations and maintain their correctness. So what we did is we collected a whole bunch of examples of uncertainty visualizations from the visualization literature and from sort of data journalism examples as well, built this collection, and then tried to figure out how do we generalize the specification of these particular different visualization types so that you can kind of formally write down a description of these visualizations and then create data visualization libraries where you can programmatically create these. So we came up with something that's a variant on something called the grammar of graphics. So the grammar of graphics is a couple of different things, but most generally, it's a sort of formal way of describing what a visualization is, its components, its data, and so on. It also undergirds a bunch of visualization libraries and even visualization tools. So if you've ever used Tableau, Tableau is built on something very similar to the grammar of graphics, kind of under the hood, in the way that it formally describes what visualizations are. If you've ever used ggplot in R, it's a library in R for making data visualizations. It's also built on the grammar of graphics, and hence its name, ggplot. So this chart right here is a rather boring chart. If you've ever heard of the MT cars or Motor Trend cars data set, this was a data set of cars from back in like the 70s or 80s. It has a bunch of pieces of information on them, things like their miles per gallon, the number of cylinders in the engine, you know, whether or not the transmission's automatic or manual or whatever. This is ostensibly a stacked density chart showing the miles per gallon of the cars in the data set, split out by whether or not the engine has 4, 6, or 8 cylinders in it. The problem is, so the way that you specify this thing is down here at the bottom. You give it a data table, and then you say you want a density geometry, which just determines what this geometry is. You provide it with some mappings, which are these aesthetic mappings or visual channel mappings just say that you want this miles per gallon column in the data table to be mapped onto the x-axis. So that's this. And you want the cylinder column in the data table to be mapped onto the fill color. So that's determining the fill color of these three stacked up densities. And then this position stack is just saying stack them on top of each other instead of drawing them on top of each other. And so then you get this chart, which should be telling me, you know, approximately the proportion of cars around, say, 15 miles per gallon with 8 cylinders, versus, say, like around 20 miles per gallon with 8 cylinders and what have you. The problem is this chart is actually wrong. So I should be able to answer questions like, at the total of all 3 of these stacked densities, what's the approximate proportion of data, proportion of cars that have miles per gallon approximately equal to 19? Or, comparing the height of this to the total height at this point, I should be able to answer a question like, what's the proportion of cars that have 6 cylinders that have mileage per gallon around 20? The problem is that ggplot doesn't know anything about conditional probability. It naively constructs these 3 densities separately and then just stacks them on top of each other. This is the correct chart. Because there are fewer cars with 6 cylinders in this data set, this region should actually be smaller than it is. But it's not, because again, ggplot doesn't know anything about conditional probability. So it does this incorrectly. You can manually renormalize the data in the specification, but now it really doesn't. The idea behind ggplot is it's supposed to be declarative. You're supposed to be able to write down things in this kind of straightforward, abstract way and have it figure out how to make stuff for you. And this really breaks that abstraction. It's kind of a leaky abstraction, and it makes it a bit of a pain to work with when you're trying to build visualizations like this. So the idea that we had was basically, can you allow people to directly specify the visualization that they want in terms of the conditional probabilities that they're interested in, and have the system figure out how to make the thing for you? If these are the quantities we want, and we're essentially trying to map these onto the height variable, why not allow people to just do that? And so we figured out essentially a way to make that work. You can say, these are the 2 conditional probabilities I want. I want them to be mapped onto the heights of these variables, and then our system will figure out how do you make this visualization. It will also guarantee that this is actually a correct visualization of these conditional probabilities. If you try to specify something that can't be correctly constructed, it will tell you that it is not possible to make that visualization. So really, this is trying to solve some of those problems with, say, like the fallacy of the transposed conditional, like I was talking about before. With this approach, we can specify a whole range of different uncertainty visualization types. We can kind of cover, I'll get to that in a second. I don't want to actually spend too much more time on the details of the implementation of this thing. If you're interested, you can see the paper that we wrote about it. Basically, like I said before, you can guarantee essentially that the probabilistic expressions people are writing down are actually correct. In this case, that they multiply to a joint distribution that is sensible. And then you can recursively construct this chart that has the properties that you can see all of the things the person has written down as conditional probabilities somewhere in the chart. We can reasonably specify a range of different visualization types, not the full range of the set that we collected before. There's really some other weird things that people do with uncertainty visualizations, like strange layouts like that risk communication theater, or parliamentary charts, or even some of these animated sorts of hierarchical visualizations like the one that I showed from the New York Times earlier. But we have a good handle on some of the base chart types, and we're really thinking about how to expand this to other layouts. We also want to include things like animation and time. But one of the reasons why I'm really excited about this work is there's a whole group of people, a whole group of data scientists and data analysts that work in building probabilistic models, where they use these things called probabilistic programming languages, where they're already writing expressions down using things like conditional probability to describe statistical models that they then fit to data. And then they have to figure out how the hell to visualize the stuff that they get out of those models, and often that is a pain. So what we want to be able to do is connect this kind of idea of probabilistic grammars of graphics to statistical programming languages that already use probability notation, and allow people to kind of directly specify visualizations using the same notation that they're already using to specify statistical models. This is also feeding back into changes to some of the other pieces of software that I maintain, like ggdist. The most recent version of that has taken some inspiration from our probabilistic grammar of graphics work, and it now allows you to map things like densities and cumulative distribution functions directly onto visual variables to create some pretty weird uncertainty visualization types. Although all of these ones, I say they're weird, but they all appear somewhere in the literature, but are kind of a pain to make with existing visualization tools. But once you're actually able to do this kind of direct mapping of distributional properties onto visual variables, it becomes quite easy to make these things and many other things. So again, this is about trying to navigate that space of what a good uncertainty visualization is and be able to kind of brainstorm more effectively. Okay. So I want to kind of take a pause for a second and step back from what I've really been talking about so far of strictly probabilistic uncertainty. And there was a question earlier about the difference between modeling polling uncertainty and actual randomness in the phenomenon. I'm going to get to something kind of related to that question in a minute. But what I've been talking about so far is all essentially forms of uncertainty that can be quantified statistically inside of, say, a statistical model. But that is not all that uncertainty is. We often kind of like to pretend that it is. So often what we do, a parody of a data analysis process might be something like this. Data comes in, analysis happens, a p-value comes out the other side, and you're done. Obviously, this is a caricature. The reality of a data analysis process is more like this, right? Data comes in, analysis happens. You have choices for things like, maybe outlier removal, data transformation, statistical models you could potentially use. There are many possible analyses you could conduct on a single data set, and many different choices you can make about what analysis is appropriate for that data set. Some of these choices may even be kind of equally defensible. And so you end up with what is a sort of combinatorial explosion of possible ways you could have analyzed a data set. And your uncertainty in what the correct analysis is one way of thinking about it is as something called specification uncertainty. So far, what I've been talking about is more statistical probabilistic uncertainty, which can be thought about in a couple of ways. So one way is parameter uncertainty. So say I fit a linear regression model to these data points here. I have a line. I also have some uncertainty in where that line is. This might be like a confidence band around a fit line. What this tells me is at every x position, where do I think the mean is? And what's my uncertainty in what I think the mean is? There's another form of uncertainty I could think about here. One would be called predictive uncertainty. So what this is telling me is at every x position, what's my uncertainty in where I think the observations will be, right? So if I took a new observation at x equals 5, where do I think, say, 90% of those observations would fall, or 80% or 50% of those observations? So this is different from parameter uncertainty. This, again, though, is all living inside of a statistical model. This is completely apart from the question of, like, is this even the right model in the first place? How well does any of this describe reality? And this is what specification uncertainty is. Of course, usually what we do is we just ignore that. We just pick a path that looks good, we publish it. The problem is often this creates bias because people pick the path on the basis of the result that they like. And I could very easily sit here and if I want p less than 0.05, I can find a specification that'll give me that. And then I'll say, oh, here's my rationale for why I picked that path. This is obviously not a great idea. An alternative is to do something called pre-registration or holdout. Depending on if you're coming from, say, psychology or machine learning, you might see different words for this type of thing, but it's basically the same idea, which is I choose a path ahead of time before I even look at the data. Then I look at the data and whatever happens, that's what I go with. The problem here, though, is kind of that old adage, no good data analysis plan ever survives the data. I learned something by looking at the data. I should be checking my model that it works for the data. I should be checking its assumptions. I should be understanding how it fits or doesn't fit the data. That will change the way that I think I should have analyzed the data in the first place, which means that I really do want to be able to sort of report the my uncertainty in all of the reasonable analyses that I think could have been applied to this data set, that combinatorial explosion of things. And now this is where we run into a new problem, which is how do I do that? How do I report that information? So multiverse analysis, one of the original papers proposing this uses things like this. So these are matrices of p-values. Every single cell in each of these tables is a possible analysis, a single possible full analysis that could have been applied to this data set in question. And then the value is just the p-value. So now what we do is we've taken like a full deep analysis report of a data set, and we reduced it to a single tiny cell in a table, and then showed you only one number. I find this to be deeply unsatisfying. Our data analyses should be richer than a single number that comes out the other side. So one of the things that I worked on was this idea of explorable multiverse analysis reports, which I will switch over to. So here, our idea was, let's allow people to, given the output of a multiverse analysis, actually explore the possible reports that could have been generated by that analysis. So here's an entire paper where you can go in and change things about the data analysis process and see how the paper changes. I might have different opinions about how I should be calculating confidence intervals, or maybe doing data transformation, or maybe even like confidence levels that I care about in this particular analysis. Why not allow the user to change those things and see how the paper changes, or even animate over, talking about this notion of hops, animating over my uncertainty due to specification uncertainty in what I think this paper should look like. One of the things you will notice is that the discussion and conclusion section doesn't change, because the idea here is not to sort of choose your own adventure, like pick the data analysis output result that I want, but to write the discussion and conclusion to be robust to the specification uncertainty in this particular analysis. Oh, someone's asking for a link. Yes, I can share a link. I'll do that in a moment. So we played around with a couple of different ways of doing this kind of thing. Let's see, we had another one where in a Bayesian analysis, you can change the prior. If you're familiar with Bayesian analysis, you have to set a prior in order to actually analyze the data, which is sort of some representation of prior information about what about the phenomenon, and that can have an influence on what your analysis result is. So the red line here is the prior, the blue is the result of the analysis. This allows you to kind of explore different priors you could set on the data, allow a reader to impose their own prior, and then see what the result of the paper would be. So part of the point that I'm trying to make here is that I think we need better ways to acknowledge specification uncertainty and actually have a conversation about it through the literature. So we've been playing around with these kind of interactive documents for doing that. I've also been playing around with a couple of other things. So one of my students is working on a library to allow people to build these things easily from R Markdown documents in R. So if you're familiar with R Markdown, or if you're not familiar with it, you might be familiar with Jupyter, which is commonly used in Python. Basically, these sort of notebook formats for doing data analysis. Why not make it so that people can directly create multiverse analyses through these notebook formats and compile them into a paper that looks like this? So we're playing around with that idea. Another one of my students has been doing, actually just completed a rather extensive literature review of multiverse analysis. One of the problems with multiverse analysis is that it is it comes under many different names across many different fields in literatures that haven't really talked to each other. So we've been kind of looking around trying to find the different sorts of visualizations that people are using to do what is essentially a multiverse analysis. And then we built a task taxonomy for these things. And now we're sort of thinking about what is the sort of full design space for to support the types of tasks that people want to do with this kind of thing. But yeah, so this is specification uncertainty. I think across all of my work, I've been spending a lot of time with parameter uncertainty and predictive uncertainty. There's more sort of statistical and probabilistic forms, and more recently have been spending a lot of time with specification uncertainty, all kind of towards this goal of building uncertainty visualizations that, present uncertainty correctly in ways that can't be ignored and in ways that people can actually understand. And that is it for my talk. Thank you.
Well, thank you. That was excellent. I think we can take questions now. There's a lot of people clapping virtually. So if you want to raise your hand in the participant window, and Matt can call on you. I think you got to a lot of the questions.
Yeah, there's oh, someone had raised their hand and then they disappeared, so now I can't see them anymore.
Should go to the top when they do that.
It went to the top and then so maybe they put their hand down. Okay. I can look at some of the questions in the chat in the meantime.
Yeah, I was going to suggest that.
The exploration format is really cool. Can readers easily compare the various model outcomes, though, since there's only one visible at a time? Would it be easier to show multiple side by side? Yeah, so that's a great question. So actually, if I go back to the example, this one. I go back. So we played with a couple of different things. One of them was based on that idea. So this is showing different estimates from different specifications. And then if you click on one of these specifications, it updates the paper to show you the details of it. There's a lot of these kind of summary visualizations that exist for doing the kind of overview of what these estimates look like. Specification curve is a really common example of it, which I think was one of the pictures in my slides. If I just go back there. Oh, we did. Oh, yeah. So this one down in the left-hand corner is a specification curve. So essentially, this line here is showing you a bunch of different effect size estimates from different possible specifications. I think that, so what this question is getting to is like, yeah, there's advantages to the overview visualization. There's advantages to the sort of document format. The document format, I think, is really important because you want to be able to see all the details of the analysis. The sort of overview gives you a better sense of what the full specification uncertainty is. So Aberneal, one of the students that I mentioned, who's working on some of this multiverse stuff, is now building a kind of interactive visualization that goes along with the document to allow you to sort of navigate it while also seeing this kind of overview. So that's kind of one of the big next directions that we're thinking about for this, because there really are those advantages on both sides of each approach. Let's see, I guess I'll go back to hands. So Elena has a question.
Hi, Matt. I'm a huge fan of your work. It's exciting to see it in this format. So the question I have, it's the same question actually Burke put in the chat. It's about kind of and I know I get this criticism from my work as well, but I'm curious about how you handle it when people say, oh, it's too much information overload, people shut down, right? So are there some kind of principles to how you put these things together that you think are more likely to, help people deal with the extra information you're showing?
Yeah, that's a really good question. So I think from the multiverse side, I don't necessarily have great suggestions yet, in that we haven't put that into practice as much. From the general uncertainty visualization side, I mean, I try to practice what I preach in terms of the way that we write papers. And the way that we write papers tends to have a lot more uncertainty visualizations in them than most papers do, in my experience, at least in HCI anyway. And the way that we try to get around this is we try to scaffold understanding a lot through text annotation. One of the papers that I most recently collaborated on with Jessica and one of her students, Alex Kale. I'm going to see if I can pull it up really quickly, because I think Alex did a very good job in this paper of kind of this particular problem. So let me see if I can, is it going to be easier to just show you an example of this? Yes. Okay, so this was a paper where we were studying uncertainty visualizations, but we also had to, of course, use them in the write-up. So before I actually show you what we did, we spent a lot of time with the communication of the results in this paper. I think Alex may have almost had a nervous breakdown at some point during the writing of this paper, just over the write-up of the results section. And we were iterating and iterating on what visualizations do we use, how do we combine the text with the visualizations. We were putting annotations in the figures, but then we were like, well, all of our annotations are now redundant with the body text of the paper. It's just like the reading experience was not good. Eventually, I had the idea that I think as faculty you can do, which is just like come up with a crazy idea and then like toss it off, and then maybe someone will do it. And in this case, the only student on the paper was Alex, so it fell to him to decide if he wanted to like go through this pain, which was why don't we surreptitiously replace an entire page of this paper with a Illustrator diagram that looks like a page in the paper, but actually has the visualizations in it, so that we can directly connect the body text to the visualizations. And so that's what he did. So if you read page 6 of this paper, the right-hand column looks like body text from the paper, but it isn't actually. This is a full-page figure. And it allowed us to write the prose such that we could directly refer to parts of the visualization as the reader is going through. The work that Alex put into this is incredible, because the thing that you have to think about is like, how the hell do you do that? Well, what you have to do is you have to make sure that the words that you want to point to the visualization end up in the right order and all end up at the beginning of a line, so that you can put an arrow from them to something in the visualization. So this is like this insane like constraint problem of like making the visualization and making the text at the same time to make this work. So I don't know if that really answers your question as to like how to make this easier, but this was one of our attempts to try to do that, at least in the context of like more complex uncertainty visualization. In multiverse type stuff, there's a couple of things. So one of the things is that I actually think that the value of the explorable multiverse idea is that you have a default analysis. If someone wants to read one analysis, they can read one analysis and it reads like a normal paper. But you're still trying to write the rest of the results in the prose to be robust to the sensitivity of the analysis. So that's one way that I think you can also solve that sort of cognitive load problem. But in general, I think with visualization, it's like annotation is really helpful. We need to use more annotation than we do. I would try to use a lot of annotation in our papers. This is like the most extreme example of that.
If I can just summarize what I took from that, is that you actually have, you're using two different modes to communicate the same information, and you're making explicit the connections between the two, and that is what's helping people get past the fact that it's a lot of information.
That is a much better summary than what I was saying. So thank you for that.
Thank you. It's a cool strategy.
Thanks. I think Rana is the next one.
Hi. Yeah. I was wondering, you talked about a few examples that used animation, and from what I understood, you were talking about the animation as kind of helping with maybe an intrinsic understanding of the visualization or the flow of time series data. Have you studied, or can you talk a little bit about how well animation in a visualization helps a user understand uncertainty versus a static outcome? So let's say the New York Times example with the race versus income, there was that animation, but there was also, once it's all played through, you have that end visualization, which you pointed out the flaws, but let's say it was correct. So maybe that's a good example to contrast.
Yeah. So I think there's a couple of things with animation, and there's sort of like some conjectures, but I think not a lot of hard evidence. So one of them, in terms of uncertainty, is some notion that we reason better about uncertainty if we are actually able to experience it in some way. And so maybe that's some mechanism by which people are able to make better decisions from visualizations like that. There are also some perceptual reasons why it is helpful, which are kind of more detailed. To actually, here, let me see. I can probably explain them a little bit better if I show you an example, although I don't have a running example, so I'm going to have to like fake it a little bit with a whiteboard. So let me
And by
let me try to do
experiencing
this.
uncertainty, you mean like that waiting for it to finish up, like the time in between when you don't yet know how it turns out? Is that what you mean by that?
Or even, yeah, or even just like some notion of experiencing the randomness of a process, right? That the outcomes can be sort of different in some way. So maybe there's actually a better example for me to try to explain this. So there's this sort of online animated stats textbook called Seeing Theory. Let me show you this example. Let's see. So this has what I would consider to be one of the better explanations that exist of what a confidence interval is, which happens to be a concept that people find very difficult for, I think, very good reasons. And I think the explanation works essentially because of the fact that it's animated. So what this little animation does is it just simulates the process of calculating a confidence interval. It takes like 5 samples or whatever it is from some distribution, say from some population, or you're running a study, you sample 5 people, whatever. You take a mean of whatever those measurements are, and then you calculate a confidence interval around it. And what this chart and what this animation does is it just does that process over and over and over again. But the value of it is that I think you can see the whole idea behind a confidence interval is it's a statement about a process. If you repeat this process many, many times, and you're using, say, a 90% confidence interval, I'll actually make it easier to see. I'll use a 50% confidence interval. 50% of the time, that confidence interval should contain the true mean, and 50% of the time it won't. And that's really just like the idea behind a confidence interval. But the process is also random, right? It's not going to be exactly 50%. If I run this a whole bunch of times, I thought there was a speed thing that made it go faster. But as I run this more and more, this will get closer and closer to 50%, right? But like, I could spend a lot of time trying to explain confidence intervals sort of using notation, or I could just show you this animation. And I feel like most people get it a whole lot better by just seeing this animation and experiencing it.
Gotcha, thank you. So I think what I'm understanding is that you're talking about the chance to experience the variety of data points that go into the end result.
Mm-hmm. Yeah. So there are other like reasons that aren't related to that, but I think this is like one of the main ones to me that I think makes animation kind of powerful. Like matches better with our understanding of the idea of randomness.
Cool, thank you.
Mm-hmm. Molly has a question.
Hi, Matt.
Hey, good to see you.
Good to see you. Yeah. So I kind of had 2 questions. So one was, I think you kind of touched upon this in your talk, but I kind of wanted to hear your thoughts on how the density of the quantile dot plot can affect the communication of uncertainty. And my second question was like presenting multiverse analysis can raise interesting questions, or spark debates around choosing between presentation of, say, multiverse analysis or doing pre-registration. So if you could, I don't know, talk a bit about that.
Yeah. So maybe you can say a little bit more about what you're thinking in the density direction of the quantile dot plot thing.
Yeah, so I was thinking like the density, or the number of dots that one chooses to present on the quantile dot plot seems to be tied to the mental calculation that one can do to take certain decisions. So is there, say, like an optimal number that one should be working with? Like
Right.
yeah, so something along those lines.
Yeah, that's a great question. So I don't know. This question, so I usually call this like, what's the denominator? Like that's the kind of question that I kind of think about this as. How many dots do you put in the dot plot? So in the first experiment that we ran on this, we did 20 dots and 100 dots as one comparison. In a later experiment, we also added like 50 dots and looked at that one as well. I think that a lot of it comes down to what the problem is, what the task is, right? Like where in that tail of the distribution are you going to generally be sort of making these estimates? Because the number, the denominator that you choose directly determines the amount of resolution that you have in the tails. It also determines which point in the tails that you can do subitizing in, right? And so if you know something about like the general like risk preferences that people have in some domain, then you might be able to use that information to kind of like choose a good denominator potentially. What we saw in at least the original experiment that we did on this was the performance of the dot plot at around 100 dots for the stuff that we were asking people basically just like turned into the performance of a density plot, which makes sense. Like as you add more and more dots, people aren't going to count stuff. They're just going to do area estimation. And then when they do that, they perform as well as a density plot, as in like they perform worse, right? So like you look at this, these two are very similar. With 20 dots, we had much more precision in terms of people's responses. But I think that is task and context dependent. Like I wouldn't say, oh, there's like one denominator that will work in all situations, because I think it depends on that where in the tail do you want to be question. So your other question was like tensions between pre-registration and multiverse analysis. Was that like the high level bit on that?
Yeah.
Yeah. This is I think a huge thing, right? There's a lot of debate going on in the psychology community right now around this question of, what's the value of pre-registration? To me, so if you asked me a couple of years ago, I was like, yeah, pre-registration is great. We should be doing it all the time. I use pre-registration in like most of my work. The more that I do it, the less strict I become about it. So I think, so one of the problems with pre-registration is that what you can do with it is you can pre-register a really terrible analysis plan. And you can pre-register an analysis plan that you will then become very confident in performing, even though it's crappy. And even though, and you could pre-register an analysis plan, which makes you have the confidence that it's the right analysis, or the right analysis, or at least that you won't have publication bias due to picking a different analysis plan. But it may also discourage you from doing something like an exploratory data analysis of your results, looking at model fit information, looking at, the predictions from your models versus the data that you have, and maybe like realizing that the model that you pre-registered was not the model you should have run in the first place. Or, something like that. And I think that this is a really kind of big problem for pre-registration in some ways, that some people kind of dismiss as a potential issue with pre-registration. In terms of the tension between that and like multiverse analysis is not a bad way of trying to address this, right? Like you can pre-register a multiverse analysis, or you can pre-register an analysis plan. So what we tend to do these days is we pre-register like a starting model and like a plan for how we're going to evaluate the model and like make modifications and things, right? And so then it's like, if you want to, you can see what our pre-registered model is, or you can see what we think the better analysis is after we understand a little bit more about the data and sort of expand the model to be a better description of the data generating process that we think is underlying this phenomenon. And then, maybe that's a good thing to do a multiverse analysis over. So I don't think that they're fundamentally incompatible, but I think that part of multiverse analysis is actually realizing the limitations of pre-registration and why you shouldn't just pre-register one analysis and then do it and then call it a day.
Thanks. Yeah, that makes more sense.
Okay.
Thanks.
Yeah. Other questions? Is there anything I've missed in the...
There was one about if you have a recommendation for data visualization books.
Oh, data visualization books. There's a lot of good data visualization books. Let's see. Oh no, I have them over here. This is a good book by Tamara Munzner. The first couple of chapters of this are excellent in terms of a introduction to the notion of visual marks and marks and visual channels as a way of like understanding visualization construction in a more systematic way. So that's a really good book. If you're just making figures for scientific papers, this is a good book that came out relatively recently. And there's a free version of it online, and the entire book was written in R, and you can compile the entire book. So it is a great book. I think those are two of the ones that I really recommend to people these days. If you just want like two off the top of my head, those are good ones as starting point. It's like I guess if it was like, if you were going to have a starting point for a book and you're interested in visualization research, this is a good one. And if you want a starting point for a book that you're interested in, like just making better figures in a scientific paper, this is a good one.
There are two hand raisers.
Yeah, there's two hands up. So Rana has another question. Go for it.
Hello again. So I'm coming more from the human factors and human machine teaming area. So thinking about using visualizations for decision support, let's say, or other kind of human machine teaming contexts, what kind of considerations do you, I don't know, study or use when it's more of a decision support versus an informative kind of situation?
That's a good question. So I think one of the things that can come into that is more like qualitative assessments of confidence when you're talking about model output. So I had a collaboration with Lace Padilla, who's now, she was a postdoc at Northwestern for a bit working with Jessica Hallman, and now she's faculty at UC Merced. She does a lot of work in like hurricane visualization and like disaster support kind of stuff. And we did this paper where we were looking at what people do if you add qualitative uncertainty descriptions on top of predictions, just things like, there's high confidence, medium confidence, low confidence in some prediction from a model. And that actually turned out to work pretty well in the experiment that we set up in terms of people adjusting their choices in like a reasonably conservative direction when we said a model had low confidence. I don't have much more experience with that kind of thing, so I don't know if I can say much more to the meat of your question, but I think that like there is a lot of value to the use of language when communicating uncertainty. There is work on these things called words of estimative probability, which has been used in, it actually originated in, I think the NSA like years and years and years ago, where they were trying to communicate confidence to policymakers, right? It's like mapping confidence levels onto things like likely or somewhat likely or unlikely, right? I think there's potentially a lot of value to that kind of approach to uncertainty communication. In terms of like visualization in those contexts, yeah, I don't know. I mean, I'm not sure how it is different.
Okay, cool. Thank you. No, those are some interesting things to think about and look into. Thanks.
Aditya?
Hi, great presentation.
Thanks.
I was wondering if you can just comment on how multiverse stats can actually improve the peer review process, especially in psychology and HCI.
Sure. That's an interesting can of worms. Yeah, like, so I think it could be valuable to have multiverse analyses in the peer review process. I think that to me, so what I actually like in the peer review process, whether or not it's a multiverse analysis, is when people give you like a supplement with an analysis notebook in it that you can run. Because I mean, too many times I've reviewed papers where I have to like make some kind of a guess at what the hell is going on under the hood. And that just makes it that much harder to review a paper, so I know some people who are very strict about this kind of thing these days. And, you know, if they have a question that would require looking at the data to answer, and they can't access the data, they just like give the paper a 1, which I think is like way too harsh. But I mean, what I prefer to do in the peer review process is like, if I have questions about something, I put that into the review and I ask the authors and hope that they respond, and then we clarify things. It's a lot easier if I don't even have to go through that loop, though, right? If the data is already there and I can look at it and there's something that I'm curious about and I can just like do it, then it's a lot easier. And the peer review process is a lot smoother. In terms of like, maybe there's like this broader question of just like, could you even publish these things? Like, can you even publish like a multiverse analysis report? Right now, it's kind of hard, right? There's like some venues that people are like, Distill, I think, is an example of a venue, if people aren't aware of it, that does like interactive sort of journal articles for machine learning. There aren't a lot of venues like that. I'm trying with a couple of folks to start one for like visualization in HCI, where you'd actually be able to publish interactive reports like this and have it be peer reviewed. But you know, there's a lot of work involved in starting a journal, and it's kind of a pain. So I'm hoping, like, you know, maybe a year from now, that kind of thing will exist. I don't know if that really answered your question or not.
I can see how it can be improved, like, especially when I review. I notice usually there are some reviewers who are hesitant to get into the weeds of analysis that papers do. And when I looked at multiverse, I thought maybe even such reviewers will have some tools to play around with and question the analysis itself first.
Yeah, well, and I think that it's like, I don't know. So when I was first like a grad student, however many years ago, actually when I was doing my master's, before I did my PhD, I also did a master's that was like kind of HCI focused. A lot of the things that faculty would tell me are like, you know, you have to write a paper in a way that like sells it, and you have to like, you know, gloss over the flaws and or the things that you're uncertain about. And I actually don't think that that's true. These days, what I try to do is I try to be as transparent about those things as possible. And I think that if you are, you can actually write papers that people like better. I think that part of it is that people just don't try to do that. They think that you can't, and then they worry about what happens if you try to. And I think that, you know, if I had some message to like PhD students out there, like, just, you know, don't bother with all that like salesman crap, and write papers that are straightforwardly describing what you think you know and what you think you don't know. And I think that you can get positive response from people by doing that.
Thank you.
I think that's a great point for ending, because we're about out of time, and that was really wonderful advice and a fabulous presentation. So thank you so much, Matt, for your talk, and for everyone who's been here, for joining us.
Thanks for having me. This was a lot of fun.
Yeah, it was great. Thank you so much. Okay, bye-bye.
Thanks. Bye.